Okay, welcome back everybody. Let's begin. We're going to get into the sufficiency principle today. We'll be talking about this throughout the class. This is obviously an important concept in statistics. So a long time ago, and I attribute Fisher for this. So you'll hear me go back and forth on things that I don't like about Fisher and then things that I do like about Fisher. Just to be clear, Fisher's in my top 3 favorite statisticians. And there's a reason why, and this is kind of one of the reasons, is that he was thinking about properties of statistics, thinking about all their mathematical characteristics, so on and so forth. The fiducial argument and the anti-Bayes regime that he kind of presented early in his career, and he was trying to substitute fiducial inference for Bayes, I don't like that part. But saying that, it all gets corrected later on. So I think Fisher, while he does have some black eyes, I would say, and they get worse than that, understanding properties of statistics is an important concept. Understanding their distribution. Understanding what you do with their distributions, quantifying uncertainties. That's not all Fisher, but Fisher is the first one that really came in and started formalizing this stuff. And so there's an interesting question. How far can I reduce my data? So I'm thinking about some statistic. What statistics can I use and still have all the information about theta, where theta is my underlying parameter set? Presumably that's what we're trying to learn from the data. In reality, usually we don't know F either. And so I want to just remind you that sufficiency is a model-based property. So if I have a model at hand, I can talk about sufficient statistics. Usually we have data in hand and we build the model. And so if somebody said, if you just had a collection of data, and they said, well, what's a sufficient statistic? You would not know. There's no way of answering that. That's a concept that applies once you have the model. Okay, so usually we have to build this up as well. And so in reality, you never throw away your data. You keep it around because you might presume the wrong model. Saying that, once we get into minimal sufficient statistics, the minimum dimensionality of the sufficient statistic, we'll be able to exploit that. And where I use it is in computation. It speeds up my code. It makes it so I have to store less, use less RAM, use less CPU time, so on and so forth. So it's a very practical concept. Fisher also asked the question, what statistics have no information about theta? And he called those ancillary statistics, and we'll study those as well. There's some interesting stuff from a mathematical perspective. You might think that ancillary statistics, statistics that have no information about theta, and statistics that have all the information about theta, they might live in orthogonal spaces, i.e. non-overlapping spaces. That's not true. And so I'll say something about that and I'll discuss Fastu's theorem, but we won't be proving that if you want to get ahead. And so I'll discuss Fastu's theorem, and the reason we're going to skip it is because I would like to include other things in this class, and there's no real practical application of it. But it is mathematically interesting. So I will be teaching you about ancillary statistics, try to clear up this confusion. I'll allude to what Fastu's theorem says, but we won't go through that proof, and I won't hold you responsible for it. Okay, so I wrote down a bunch of definitions. All of these are in the book, and while I think this is a terrific textbook, but it's all over the place. There's a lot of concepts. They're trying to cover a lot of material, and I find this to be one of the most jumbled proofs in there. And if you've read through it, maybe you agree with me, or maybe it's just obviously transparent to you. I'm going to be talking about the steps of the proof, and they do it in this framework of 2 experimenters, and I'll introduce you to the 2 experimenters. Let's just kick it off. So some definitions. So statistic, T of X, X is data, is a form of data reduction. I think what we mean is like the dimensionality is reducing. So it's just a quick example that you can hold in your mind, and we'll keep referencing this example and we'll reference it through the proof, is think about this Bernoulli example. So if I write out the joint distribution, I could write it out in product form, I could write it like this, and I could compute it like this. And if I were doing that on a computer, that would be a lot of work at every step, or I could compute everything like this, where I just store these sum of xi's. And so sum of xi's, this function only depends on the x's through the sum of the xi's. I don't actually need the ones and zeros. I just need their sum. So the data is n-dimensional. The sum of the xi's is one-dimensional. So we'll just point that out. So that's what they're talking about. So when they talk about data reduction, I think this is kind of an old term. We don't really talk that way anymore. But there's a dimensionality reduction. The question is how far can we reduce without loss of information about theta? We're not going to answer this question directly right now, but when we get into minimal sufficient statistics, we'll answer that question. I'll give you a formal definition of minimal sufficient statistics, but just to point out, P is one-dimensional, sum of the xi's is one-dimensional. I can't reduce the dimensionality of that statistic any further than one dimension. There's no such thing as a 0.3 dimensional statistic. It's a discrete object that I have to hold it. And so there's no way you can reduce this any farther. So that is minimally sufficient. It's the minimal dimensional sufficient statistic. We'll be trying to answer this question formally. Sufficiency principle. So this is the stuff that kicks off chapter 6. So let's just read through some of these definitions, see if we understand them. If T of X is a sufficient statistic, then any inference about theta should only depend on X through T of X. That makes sense, I think. You can just look at this example and see that this function that you're going to be doing inference off of, presumably, only depends on X through the sum of the xi's, right here. So all I need to know is the sum of the xi's. I don't care what the order of the ones and zeros were, so long as you tell me everything was IID, it's exchangeable. We know that. So I don't actually care about where the ones and zeros wound up in the sequence. All I care about is their sum if I believed everything was Bernoulli and IID in the beginning. I could just use also the binomial formulation. I'll just point out that this right here, sum of the xi's, I'll just write down its probability distribution, F sum of the xi's, given P. This thing is N choose sum of the xi's. P to the sum of the xi's. 1 minus P to the N minus sum of the xi's. This example that we just keep coming back to. So that's the binomial representation of all that. Okay, so I think it does kind of make sense that I can base all of my inference off of sum of the xi's in this example. And that's what they're talking about right here. So sum of the xi's is a sufficient statistic. I'll point out also, I could have written this out like this. So I could write this as P to the sum of the xi's where I goes from 1 to, I'll say, n prime, plus sum of the xi's where this goes from n prime plus 1 to n. I could have written it out like that. I'm just summing things up and I'm breaking it into two terms. So 1 minus P to the n minus this same thing. We'll just drop that in there. So that's exactly the same. So in that sense, this thing right here, sum of the xi's plus sum of the xi's, you have to pay attention to the indexing here. I goes from 1 to n prime plus 1 to n. So I'm making an assumption that n prime is less than n in all of this. This thing right here is also a sufficient statistic. It's two-dimensional, but the data only depends on everything through these two terms. So that's also sufficient statistic. Just to keep in mind, some of the xi's themselves are also sufficient statistics. So this function depends on the data through that. So later on, we'll answer this question about reducing it minimally. As long as I can compute the sum of the xi's, I have a sufficient statistic. We'll use that definition when we get into min sufficiency. Okay, so I think this definition makes sense. The next thing that they write in there says a stat T of x is sufficient if the distribution of x conditioned on T of x does not depend on theta. So at that moment I get lost. I can remember reading this and thinking, I got the first thing. What the heck is this second thing? So why is that obvious? That these are the same. So if T of x is a sufficient statistic, that any inference about theta should only depend on x through T of x. Makes sense to me? Now they're saying it a little bit more mathematically, but they're writing it out all in words. A statistic T of x is sufficient if the distribution of x conditioned on T of x does not depend on theta. Can somebody explain to me why that's true? Or do you get it? It's just too obvious and we can just conclude and move on to chapter 7. Does it make sense?
Because T of x is a sufficient statistic about theta, so then if we condition x on T of x, it shouldn't require us to know theta.
You just repeated exactly the words written on the board. So you read it to me. I can also read.
I thought it made sense.
Here, let me do my excellent teaching job. A stat T of x is sufficient if... Here, let me say it again. I'll just say it slow. Can anybody give me any conceptual rationale why that might be true?
Is it just because you can infer everything about theta through T of x?
I mean, it is. That's what they're telling us. That's true. Why?
The x is displayed the x is dependent on theta, they display theta themselves, so we can then just go back. The one applied the other.
Why?
It is so.
Okay, I like that too. They sound like some of my old professors. Because I said it! Swallow the pill. Let's just think about this example real quickly. How do we even compute this distribution? So if I'm going to take f of x, if I want to compute this thing, T of x, and I'm going to write it out with P in there. If I were going to compute this, all I need to do is I need to write down the joint distribution of x and T of x, given P, and divide by this distribution, T of x divided by P. So by definition, this is what that conditional distribution is. So let's just think about this conditional distribution right here. And think about how we compute this thing in the first place. So I want to point out real quickly, and we're going to recycle this 2 times in our proof. I'll get rid of this. That's the easy part. I just want to remind you that f of x and T of x, if I think about this joint distribution right here, this is exactly the same as f of x given T. If I have the data, I can compute T of x. It's not a probabilistic calculation. There's nothing random about it. So if I have the sum of the xi's and they're random, and I want to understand what the joint distribution is of that random thing and some deterministic transformation of it, I don't change the probability distribution of anything. If I know x, I know T of x. They're exactly the same. So there's no uncertainty in knowing t of x when you know x. So if I gave you a vector of ones and zeros, you could compute its sum, and you wouldn't have a change in the probability space. You just compute its sum, that's all there is to it. So this presumes you can add up numbers and not make errors along the way. And so these are equivalent to each other because there's no extra information. For loss and computing t of x from x. Same exact thing. So what's this distribution in the numerator? It's just the Bernoulli thing. And what's the distribution in the denominator in this example? It's the binomial thing. Let's take the ratio of these two things for this example. So if I take this ratio of this to that, all I'm left with is the normalizing constant. And so this thing right here is n choose sum of the xi's. I goes from 1 to n inverted, because it's in the denominator. And so let's just glance at this thing real quickly. For this specific example, we notice that this does not depend on p. That's what they're talking about. So to really understand this, you just have to understand what that conditional distribution is. You think about how you compute it. Here's an example of that. So this is the way I really think about it. So it's really just the joint distribution over the distribution of that statistic. So I'm taking a ratio of the distribution of the statistic, and I'm dividing it into the joint distribution. And that's all we're doing to get that conditional distribution. And that's because there's no extra information in computing something once you have the whole vector of numbers. So it doesn't depend on theta, so I can get rid of this right here. There's no p in this formula. And the p drops out. There's no, well, I'll leave that p in there. But there's no p over in this conditional formula. How do I know? Because I computed it and there's no p. The way I think about this conceptually is these two functions as a function of p, they have entirely the same dependence on the data. In both I should have probably written it out like this, but you get the point. Everything cancels. So the dependence on x's through p is entirely the same in both these formulas. They have the same shape in terms of p, and so they cancel each other. And that's what I've been talking about the whole time. If the likelihood functions have the same shape, you're getting the same information. Now, I am saying that in a way that alludes to the likelihood principle, and the likelihood principle, as you'll find out, is a statement about both the sufficiency principle and what's called the conditionality principle. And so the likelihood principle relies on the sufficiency principle, i.e. the shapes of those likelihood functions are the same. If the shapes of the likelihood functions are the same, they have the same information about the parameter. That's the way I think about this intuitively. So, and what does that mean? Here's one way of expressing it. F of x conditional on the sufficient statistic does not depend on p. That's another way of saying the exact same thing. So, likelihood shapes are the same, that will happen. Does that make sense? Okay, good. So, this is all I really want you to know. I think we could move on and gloss over forget about the proof that they wrote down in a sufficient statistic if we just define it that way that, well, their shapes, their dependence on p through the data is exactly the same, so in the ratio sense, everything cancels. I could have said it that way. And this is just kind of a cleaner way of saying everything, but you have to think about what this calculation is. The only way I can think about this is by defining what that conditional distribution is. The conditional distribution is the ratio of these two distributions. Their dependence on P through the data is exactly the same, and so that part cancels out, and there's no dependence on the parameter, P in this example. Okay, cool. Let me just ask, what kind of distribution is this? This is a distribution, f of x given t of x. And I just wrote it down. And choose some of the xi's. What distribution is that? It's not geometric. So geometric has keys in there, right? You need a probability inside of it. So there's no key in there. There's no, it's not geometric.
What was the question?
What distribution is this? For this example, I've written it down. And choose some of the xi inverse. What's inverse? Yeah, there's an inverse there. You just, if I take this and I divide it by that, I just have the normalizing constant down at the bottom. This is some of the xi, so I'll just write this down so we can all see it. F of x given t of x, and I'll write down the key. Usually you plug this into this formula to verify it. This is equal to 1 over n choose some of the xi's. It's just that thing. What dist is that?
I can see it looks symmetrical with a U shape, but I'm not sure how it's going to be. No?
It's 1 over a number of things. It's uniform. This is a uniform distribution over these sets. That's all it is. It's the number of ways that I can organize ones and zeros such that the sum of things is sum of the xi's. So if I took a whole bunch of different vectors of ones and zeros, so long as they all sum to the same number, they have the same number of ones in there and the same number of zeros, and I scrambled them, and I enumerated every single one of them that I could. How many are there? It's n choose some of the xi's. That's how many of those there are. If I took those vectors and I put them all into a hat, and I shook them up and I reached into the hat, and I grabbed one of these vectors of ones and zeros, such that the constraint was the ones summed to some of the xi's, that's a uniform distribution over those vectors. Does that make sense? Cool. So it's just uniform. Jen?
Professor, what you said makes sense to me, but I'm struggling to find a connection between the sum of the xi's and x. So if that sum changes, doesn't that...
But the sum won't change, because it's going to be constrained on it. So there's no key in here. But this is conditional on that being true. So this is going to be such that the sum of the xi's is equal to a particular value.
I see what you mean.
So that has to be enforced. So that's a constraint. So this is a particularly easy distribution to sample from. Shall we meet the two experimenters? This is your proof. And I want to read through this a little bit. Has anybody read through this argument in chapter 6? 1. Congratulations, Eric. I want to remind you I'd rather teach and not preach, but why not take a moment for a second? Being one day ahead and one day behind in college or graduate school is the difference of 2 days, but the learning experience is wildly different. So if you're coming in and you kind of know everything already, you've already read through everything, which presumably you will do eventually anyway, you only need 2 extra days to do that. And then you get to see things twice instead of the first one you wasted. Should be obvious, but that's the way I think about it. Okay, back to teaching. Let me read this real quickly. A sufficient statistic captures, this is on page 272 and 273, and there's a mathematical equation that I'm going to highlight for you, and this is where everything gets really muddled in their proof. And understanding this passage is necessary to understand the proof. That's what makes it hard, is usually we skip to the math and go, okay, that all looks right, but you don't understand what the symbols mean. So let's read through this, and I don't love the symbology that they use, but I'm not saying that they're incorrect. I'm going to change their notation slightly. So a sufficient statistic captures all the information about theta. Consider experimenter 1. Experimenter 1 observes x, and of course can compute t of x. Let me write that down. So they get to know two different things. So experimenter 1 gets to observe x. This is what they really get to observe. This is their random variable. And we're going to be specific about this notation. And this is where the proof gets a little bit muddled, is understanding what the random variable means and what the instance of the random variable is. So they get to observe this data. That's the actual data. This is experimenter 1's random variable. And of course, they can compute t of x. So they can take this data, if this is this example, it's the sum of, they get to see the vector of ones and zeros, and they can compute the sum. Okay, back to the passage. Now consider experimenter 2, who's not told the value of x, but only that of t of x. So they get to know the sufficient statistic. So experimenter 2 gets to observe this thing, t of x. They don't know x. I'm going to read through this a little bit more. Consider experimenter 2, who's not told the value of x, but only that of t of x. Experimenter 2 knows, this is the important part. If you miss this, it's gone forever. It's actually in the book. Experimenter 2 knows p of x equals y given t of x is equal to t of x. Okay, so there's a cap x in there and a little x. So experimenter 2 knows p of x is equal to y. So they write down, I'm going to write it with f's. They know f of x is equal to y given t of x is equal to t of x. So they're saying they know this model right here. And the question is what is that random variable and what is that? But this is the way they write it out in the book. And then they go on to say, thus, experimenter 2 can use this distribution and is satisfying p of y is equal to y is equal to p of x is equal to y conditional on t of x. So they're saying this thing right here. So experimenter 2 can compute again, this is all in the book. F, and I want to write it down exactly the way they wrote it. And we'll change the notation a little bit. Y is equal to y given t of x is equal to t of x. And they say this thing is equal to f of x is equal to y And they changed this notation another 2 times in the proof. Kind of drives me crazy. But there is an important sentiment out of all of this. So they tell you, and you have to swallow this when you read through it, that experimenter 2 knows this thing. I'll say a few more things about it. So thus, experimenter 2 can use this distribution in a randomization device, such as a random number table, to generate an observed Y satisfying that condition. So presumably, experimenter 2 has this random number generator. So where does that come from? How do they do it? What are they talking about? And so this is the difficult part. And what they're really saying, and this is the key part, is that these 2 distributions are the same. Here's what we really mean, and we really need to explain this a little bit better. This is going to be experimenter 2's random variable. And they can generate random variables given they know what T of X is. So let's just think about what they're saying. What they're saying is if they know T of X, they can go back and glance at this distribution, and I'm going to just change the name of this thing and call it a Y right here. So just to denote experimenter 2 is doing this. What they're saying when they enforce the equality sign with the cap X is that they have the same information essentially, and those random distributions are the same. And I think that they probably could have said this a little bit easier. They also have some butchered notation that they say, also this is a distribution on the set with a particular constraint, and they write out the constraint. But they don't write it in the conditioning block, right here. I'm going to write it right here. That's equal to T of Y. So these are equal to each other. So these random numbers that experimenter 2 is going to generate, they're going to generate random numbers such that T of Y is the same as the constraint that experimenter 1 sees. It's exactly the same thing as T of X. Let's see how they do it in this example. This is what experimenter 2 will do. They'll go to this distribution. So experimenter 2 gets to see F of Y is equal to Y, given, I'm going to write it out like this. Given this constraint, they do not write that in the book, that T of Y is equal to T of X. They do write it in the paragraph form, though. You have to read through it and understand what their notation is, but I guarantee you, if you just read through the math, you wouldn't understand what it meant. So, they can sample from this distribution right here. What is this distribution? They know it. It's n, choose sum, and now I'm going to write it out with y i's. I goes from 1 to n, inverse. It's that uniform distribution. So experimenter 2 can go to that uniform distribution. You tell experimenter 2 what some of the xi's are, and they'll create a lot of vectors, size n, with the number of 1's being in there, the sum of the xi's, and they'll do every permutation of that. Reorganize it, they'll throw it into a hat, and experimenter 2 will go into that hat, pull out a vector, and that vector need not actually be x. It just needs to have the same constraint. The sum of everything sums up to what experimenter 1 sees. So it doesn't need to be the same vector. It just needs to be a vector with the same property. So experimenter 2 can sample a new vector, and what they're going to show is that vector has the exact same information about P in that example. So you have to believe experimenter 2 in all these examples has a randomization device that they can sample from whatever the distribution is. What makes this hard is that in other examples, their next example where they look at normality, it's not uniformly distributed, what they're looking at. And it's a much harder distribution to sample from. And I remember thinking to myself, where the heck do they get that number table from? You can just generate numbers. So let me give you, or at least let me query you guys. Do you guys know of any general sampling distributions or sampling devices that if I just told you the mathematical form of the distribution, you could sample from it? Which one? What is it?
There's a few in the book.
Yeah. So if I gave you a density function or a mass function, if I gave you its mathematical form, and that's what experimenter 2 can write down. So we failed to mention they both know the model. So both of them get to see the model, otherwise the concept of sufficiency doesn't exist. So if I gave you a mass function or a density function, you need to compute the joint distribution. How would you sample from it in general? Sam says there's a few suggestions in the book. So I make a claim I can always do this, no matter what. And it's just a question of speed. So one answer is Metropolis Hastings. So Metropolis Hastings is one such device that if you gave me the actual formula, something like this, I could sample from it. Some of the other ones in the book are faster, maybe than Metropolis Hastings in some cases, and they have constraints on when they can be used. Like inverse CDF works well in one dimension if you can compute the CDF and invert it. Okay, Metropolis always works. So you're thinking Metropolis. When we get into the next example, I'm going to offer you an extra credit homework problem where I'm going to ask you, if you'd like, to code up Metropolis Hastings and run it on that example and pretend like you're experimenter 2 and show what experimenter 2 would do. This really had me baffled many years ago, where how do I know that they can do that? Not because I didn't know how to do it. Okay, now I do know how to do it, so now this step of the proof is illuminated. I could do it, I can imagine that. So if you don't know that if I gave you the sampling distribution, the mass function or the density function, and you could sample from it, you just need a Monte Carlo class. But Metropolis Hastings is one such algorithm to do that sort of thing. Okay. We can conceptualize it a lot easier in this example where I can just imagine taking these vectors and placing it into a hat and grabbing at them. In the next example, we'll talk about it and slow down a little bit, and then I'll offer you that extra credit homework. So wait until Monday and I'll describe that. Okay, so this is what they're saying right here, is experimenter 2 can draw a vector y such that t of y is equal to the constraint that experimenter 1 sees. So they can always draw from this distribution. And they end up calling that this, right here. So they say they have the same random variable, or at least these probability measures on these two different random variables are the same. So I don't love that part, that they say it like that. I wish they just stuck with y. That would make me happier. Here's the proof. Let's leave that in there. Now let's walk through the steps of the proof. When I read this proof the first time, I understood every mathematical step. I could probably regurgitate it, but I did not understand it. And there's a big difference. And so that would not let me sleep very well that night. And so I woke up in the morning, I asked my office mate about the proof. He said, Scotland, it's obvious. I said, it's not obvious. What is this step? And then he sat quietly for 4 hours and then told me it was obvious again. It really was that conversation. Okay, let's go through it. So we're going to show f of y given theta is equal to f of x given theta. Okay, y is experimenter 2's random variable, and x is experimenter 1's random variable. And if you don't read through that paragraph, you will not understand what their proof is really saying. But hopefully you can keep all this in mind, and I'm going to change the notation slightly. But we want to show that this vector that experimenter 2 can generate has the exact same information about theta as what experimenter 1 has. And I think it's starting to become obvious what is going on here. The proof is a little bit weird. It follows this 1960s classical form where you have two people in an argument and then they agree. So this is kind of a philosophical norm for proving things, doing deductions if you're into that sort of Platonic literature. I am not. But I sort of read a lot of it. Okay, so here's the proof. So experimenter 1 has this distribution. So they can compute that, the joint distribution. They know the model, they know X, and so they can write this thing down. So that would be like them writing this down, which is just that. This is f of x. I'm going to be a little bit more specific. I'm going to write down that they've got this actual observation x and t of x is equal to tx, given theta. No extra information. This is just extra calculation that I'm producing. So from my vector of 1s and 0s, in our example, I can compute t of x, the sum. So this is going to look like this. F of x is equal to x, given t of x is equal to t of little x in theta times f of t of x is equal to t of x given theta. So those are the same things. So if you've taken probability class, if somebody showed you this and they didn't tell you what anything meant on the board, you'd say, yes, that's correct, that's true. So I don't need context to understand that, everything's been written out. So if I multiply by its distribution on the thing it's conditioned to, it gets upgraded to its random variable, everything's conditioned on theta right here. T of x is sufficient. So just note up here, T of x is sufficient. I should have said that up front, but that's the only thing we're talking about today. And so because T of x is sufficient, this distribution right here doesn't depend on theta. What is this distribution? It's the ratio of the joint distribution to the distribution of the sufficient statistic. They have the same shapes, so that's gone. So since T of x is sufficient. That's not there. Here's the hard bit. They write this. F of y is equal to x. Right here. This is what's written down in your book. So given T of x is equal to T of x right here, I'm going to give myself a little bit of room there, times f of T of x is equal to T of x given theta. They just introduce, they throw in experimenter 2's random variable right here. I would prefer if this wasn't an x. This is a true statement though. So experimenter 2, using this distribution, this hat, in the binomial example or metropolis and other examples, could have generated this value of x with the same probability that experimenter 1 saw it. And that's what they're saying. But keep in mind what they wrote over here. They have the y here. I remember being like, what the heck? And it's because both things are true. And so this could have been equal to a y, and I would prefer that. But in the book, they write x right here. And what I would do is I would write down that this is equal to t of y right here. In the paragraph that you read prior to the proof, they tell you about that constraint, and they explain it in words, but it doesn't show up notationally in their proof. So this is the part that I didn't understand. Why can't I just slot in their random variable right there? That's not what's written right there. It's not what's up front earlier. It's a slightly different thing. And notationally it is different, and conceptually it's a little bit different too. That experimenter 2 can generate any y, they just could have created x with the same probability that experimenter 1 saw it, but they didn't need to generate the same x. So they could have generated any of these vectors with the ones and zeros adding up to some of the xi's. It doesn't matter that it was the same one. And so I like that, and I like that right there to remind us what the constraint is. This is also equal to T of y. We don't need to know that, but they are the same. And so this is the important elusive part of everything. This requires a randomization device. So i.e., experimenter 2 can sample, can use Metropolis, Hastings, or something like that. And that's why I asked you to do that problem in the book. So at least they don't prove that that sampling technique works. They don't say much about it. So it's still a little bit of faith that this thing works. Later on, hopefully I get a chance to show you how all these different samplers work and how you use them in practice. But now we're basically done. And so all we're going to do is rewrap this up, repackage it by taking this, multiplying it together, upgrading it to the random variable. So this is just going to be y is equal to x, or I like y right here. I'm going to get rid of that. So I don't care what you call this because they're the same things. So t of x is equal to t of y. And I could have called that cap t of y because of the constraint. They're exactly the same. So given theta right here, so I just multiplied this through and just convinced myself these are the same random variables because they get to see the same summary statistic. And this thing right here is just f of y is equal to, they would write it down as x in the book, but I write it down as y. Because it doesn't have to be the same object. In this vector right here, y has the same information about theta is x. So these are the same things. And that's the proof. So let me just summarize real quickly. Experimenter 2 can generate a random vector from this distribution. And again, they can write this down. So they can write down the map for this thing right here. In our previous example, it's that uniform distribution. He can sample from that distribution, and that distribution has the same properties, the same inferences about theta because it's the same probability model. I don't care that you, this is the way you think about it. You can think about it as just this ratio form, and the shapes, the likelihoods are the same, so they have the same information. And that is what this distribution is. But I would like you to try to understand what these various steps are, because I think it's a good thinking problem. We're going to come back next time, and we'll jump into the factorization theorem. That's on Monday. But this is where I'll close everything off for the midterm. So we're going to have a midterm on Wednesday. I did ask you last time, would you like to take home or in class? I have it from lots of sources. Many of you would like it in class. So we're going to stick with that. So there's advantages to both. So in class, midterm on Wednesday, and we'll make it shorter. And that's probably why you guys like that. So that's okay. I'll see you on Monday. We'll go through the factorization theorem. If you want to get ahead and see that, you can do it. It's a fairly obvious theorem. But it's actually how you recognize sufficient statistics. I'll point out right now, all we have from our definition is if I gave you a if I gave you a statistic, you have a mechanism for verifying if it's sufficient or not by looking at that ratio. And so far, that's all we have, which is a little bit different from if I gave you a model, how do you recognize the sufficient statistic? Okay, try to clear that up next time. Thanks, you guys. Have a great weekend.